Section 2.2, we're going to start talking about polynomial equations. You'll notice it says day 1. We're going to actually talk about this for 2 days, and I tried to find a reasonable sort of place to split it between days, and so that's what we see happening here in these 2 lessons. So to start with, you need to know, or remember really, the zero principle of multiplication. So the zero principle of multiplication says that if a times b is 0, then either a is 0 or b is 0. In other words, you can't multiply 2 things together and get 0 unless one of them was 0 to start with. That may seem like an obvious fact, and I think it's fairly reasonable when you look at it. But the reason that we're mentioning it here now is because it actually helps us to be able to solve quadratic and in general polynomial equations. So here are 2 examples of that. You see 2 pieces of information, each inside of parentheses, that are multiplied. That's what the parentheses mean. And it's equals 0 on the other side. Okay? So the reason that what you remember, and I'm sure you remember it from algebra, either algebra 1 or algebra 2 or something like that, setting each of these equal to 0 and solving is because of the zero principle for multiplication. The only way this equals 0 is if one of these is 0 to begin with. So we're going to set each of them individually equal to 0 and solve. So you have 9v plus 3 equals 0. I'm sorry, 5v plus 3 equals 0, and 9 minus v equals 0. And that at that point, they're just linear equations like we were working with in section 2.1. So we're going to add or subtract things, we're going to divide by things or multiply by things, and we're going to solve for the missing or for the remaining variable. So we'll start by subtracting our 3. So my positive 3 and my negative 3 add to 0. That's my goal. On the right-hand side, 0 minus 3 would be negative 3. And then we would divide by 5. So one of my solutions, I'll write it over here, is that v equals negative 3 over 5. Does that make sense? Okay. The other one, again, my goal is to get v alone. I can either move the 9 or I can move the v. I'm going to choose to move the v this time because it's negative, and if I move it, I have to add it to the other side, making it positive. So I can do this in one step, and 9 equals v. If you want to move the 9, that's fine. You just have to remember then you have to either multiply or divide by a negative to get the v alone without the negative in front of it. So my second value is that v is 9. And those would be the 2 solutions that I have for this particular problem. It is possible that the 2 parenthesis pieces would be identical. And if they did, you might not get 2 answers because they're actually just the same answer twice, right? But typically speaking, you get an answer from each set of parentheses that's there. So it makes sense that we would get 2 answers here because it had 2 sets of parentheses to start with. Okay? All right, on the next one. You'll notice that you have this negative 4 in front, right? Well, in theory, you're welcome to write down negative 4 equals 0, y plus 3 equals 0, and negative y minus 5 equals 0. But the reality is that this is sort of not necessary. Why? Why do I really not need to write down that piece at the beginning? Nobody wants to tell me that negative 4 does not equal 0? Right? I mean, it doesn't. There's no way in any universe that negative 4 is equaling 0, correct? Yeah, so I can write it down, but it doesn't solve. Like, it's no solution. It doesn't give me any value for the x in this problem, or y's in this problem, for the y, because the negative 4 doesn't have a y attached to it. So there is no solution from here. What that means is you don't really need to write down any constants that are all by themselves pulled out, set equal to 0, because they can't equal 0. It's not possible. However, the other 2 pieces could. So we would subtract the 3. So one option is that y is equal to -3. And on the other one, you can either add the 5 or add the y. I'm going to add the y because I can solve it in one step if I do. And -5 equals y. So I have two solutions. Y equals 3, -3, -3, and y equals -5. Okay. How can I check to make sure that these are actually really solutions? Yeah, you're right. I could take them one at a time, and I could plug them into the equation. So in the case of the first one, like right here, I could take -3/5, and I could evaluate into the equation for all the v's, -3/5, and I could make sure that it really equals 0, the whole equation. I could do the same thing with the 9. I could put the 9 in for all the v's, make sure that all of it actually ends up equaling 0, and so forth. So I can always check to make sure that my process actually worked at the end if I choose to do so. So maybe you don't want to do it on a regular basis, but maybe on a quiz you might choose to, or on a test you might choose to, right? Just to confirm and make sure that you didn't make a mistake. Okay, so 1 and 2 are actually kind of nice because they were already in these parenthesed pieces. They were already factored. But they're not always factored, right? Sometimes we end up with polynomials that are not factored form. So one of the issues with factoring to look at is to consider if all the terms have something in common, like every term has something in common. And if so, then we would factor out that greatest common factor. Okay, so does everything have an x in it? If so, we factor out an x. Does everything have a 5 in it? If so, we factor out a y, etc. Whatever it is that they all have in common. So we'll do an example of that, a couple of them actually, with 3 and 4. So on number 3, what do 6u squared and -12u have in common? You're right, Avery. They have a 6 and a u. So we're going to pull out 6u. So if I were to take the 6u squared and I were to pull out 6u, what will still be left? There will be a u from that piece. Slow down on for just a second. But yeah, from that piece, there will be a u, right? 6u squared, I pulled out a 6, I pulled out a u, there's still a u there. Now the sign stays the same in the middle, and we'll do the same thing for 12u. So if I have 12u and I'm pulling out 6u, what's left? A 2, right? There's still a 2 that's left. So if I'm working with this problem, and I see that they both have the common factors, I pull those pieces out. These are the two different polynomials pieces, factored pieces, that I end up with. And now I'm kind of back on the same point that I was when these problems actually began. Right? Now I realize that there's no parentheses around the 6u. Put them there if you want. It doesn't hurt anything. But they aren't really necessary either because there's no addition and subtraction. And I'm going to set each piece equal to 0. So in the first piece, if I divide by 6, what will u equal? 0, right? On the second piece, what would I do? I'd move the 2 over by adding a 2. So u is equal to 2. Okay, so there's two answers. U equals 0 and 2 for my solution set. On number 4, what's different than what happened on number 3? You're right, it's not set equal to 0. And the 0 principle only works if it's set equal to 0. So the first thing that we have to do is we have to shift things around so they do have a 0 on one side. It doesn't really matter which side I have a 0 on, but it's kind of friendly to put it over here on the left-hand side, so that's how I'll move mine. All right, so I have y squared minus 19y, and then on the right-hand side, the whole point is that this is 0 over here now, right? So, zero principle only works if it's set equal to 0. Now it is, so I can do the same thing I did on the previous problem. I can look and see what do these two have in common. Sorry, that's not supposed to be there. Fix that if you did that with me. I'm so sorry. This should be negative 19y. Okay, so what do y squared and negative 19y have in common? Just a y, right? Nothing more this time, just y. If I pull a y out of y squared, what am I left with? A y. And if I pull a y out of negative 19y, what am I left with? Yep, negative 19. I would set each piece equal to 0, which is kind of nice because one of them is already solved, right? And then on the one that's not, we'll add our 19. So y is equal to 19. So two values. Y equals 0, and y equals 19. Okay, are we good?
Wait, so why does it equal 0 on that one? Why does y equal 0 again?
Because the first piece was set equal to 0, and it just didn't have anything with it to shift. Yeah.
And then at the top where it's equal 19y.
Yep.
So like I was thinking, how can you divide because it's like multiplication?
Let me actually show you why that I didn't divide. It's specifically because what's there. Am I off the screen? Not yet. It's specifically that what I would want to divide by, Reed, is y, right? Okay, so let's say I divided by y. Don't write this down because it's actually wrong. I'll show you why it's wrong. But we would get y is equal to 19, right? That's not the only solution. Y equals 19 is a solution. That's true. But look back at the original equation. Isn't y equals 0 a solution as well? If I put 0 on both sides, wouldn't it work? It would. So the basic rule of thumb, Reed, is that we don't divide by variables because when we do, we usually lose a solution in the process. So if we had done that to divide by the y, we would have lost the solution y equals 0, which is definitely a solution to this equation. So this is a no-no, if you will, because we lose solutions when we divide by variables. All right, so I keep using the word polynomial, but I haven't actually defined it. So we're going to talk a little bit about polynomials and what polynomials are and what they are not. So for example, to start with, I'm going to give you some things that are polynomials and some things that are not polynomials. And then we'll kind of talk about the basic form that it has to look like, or what maybe it can't look like for it to actually be in the right category. So an example of a polynomial would be something like 1/2 x squared plus 2. Or 3x cubed minus 7. Or 4x. It can just be plain old 4x. It could be 6x to the 4th plus 2x squared minus 1. These are all polynomials. Okay, so these are the non-examples that I have for you. X to the negative third. Square root of x plus 2. 1 over x plus 7. You can either say it positively in terms of what do I see happening in polynomials, or you can say it negatively in terms of what do I not see happening to polynomials. But somebody tell me some patterns that you notice between the things that are and the things that are not. Tell me something, anything. Y'all are not talking to me at all this morning. Help me out here. What do you see in common on the polynomial side, or what do you see that I'm not allowed to have on the polynomial side? Okay, say it louder, Avery.
It's all positive.
All positive numbers in general?
Well, I said exponent.
Exponents is what I wanted. I just want to make sure I heard right. Yep, all positive exponents. Do you see that? Yeah, we need positive exponents. Negative exponents are a no-go. Okay, what else? You're about to say something for me, Caleb.
Square roots.
Yeah, the square roots are also not allowed, right? So we've got negative exponents that are not allowed. They need to be positive. Square roots are not allowed, at least with variables underneath them, right? And that's true. No square roots. And what's the last piece that you see?
Variable in the denominator.
Yeah, variable in the denominator. So it's a little bit confusing to see because I do have a fraction here and I do have a fraction here. But the difference is that one fraction that's allowed is a number on top and bottom. The fraction that's not allowed has a variable on the bottom. And that's a true statement as well. So I need positive exponents, I need no radicals, and I need no variables in the denominator. That's what I would be looking for something to be considered a polynomial. Now the general expression that our polynomials is written down there. It's a sub n x to the n plus a sub n minus 1 x to the n minus 1 dot 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 down to a sub 2 x squared plus a1 x plus a0. All those a's are just numbers. It's just, I mean, I run out of letters of the alphabet basically is the idea, because you could have not infinitely many of them, but you could have plenty of them, more than 26 even if you wanted. We won't, but we could. So they're just letters, okay? They're just numbers. Those letter A sub whatevers are representing numbers. And then those x's are just representing positive exponents, x to a positive exponent. So if you want to think about one that you've seen before, probably, ax squared plus bx plus c. You've seen that before, right? Yeah, that would be a polynomial. But there's nothing special about the powers being 2, 1, and then have a constant at the end. It's just one of the many in that category. Now, specifically, that last one that I just wrote down has is a general type. It's actually good grief, it's actually a quadratic equation. So a quadratic equation is an equation of the form ax squared plus bx plus c. It is a polynomial, and it has a power of 2 in it, x squared. The one condition is that the a cannot be 0. I should say that. If a were 0, I wouldn't have an x squared term, so it wouldn't be quadratic. But other than that, b could be 0, c could be 0, those would be okay. And a little bit of vocabulary regarding polynomials. The first piece, there's 4 pieces here. The first one is leading coefficient. The leading coefficient is the coefficient of the largest degreed term. So degree is just the exponent. So the largest exponent term. So on this one, the leading coefficient is actually leading, like it's in the front. But leading doesn't necessarily mean that it's in the front. It just means it's the coefficient on the largest degreed term. Okay, so this one is it because x squared is my biggest power, right? X to the 2. So my largest, so my leading coefficient for that term would be a. Let's do a few more. A monomial is a single-termed expression. I gave an example of that earlier on the polynomial side. I wrote the example for x. So that's just an example. Okay. So what does it mean for it to be a single term? Well, it means there's no addition or subtraction separating it from another piece. That's what it really means. A binomial is a 2-termed expression. So I had done one of those as well underneath the polynomial side. I'd written 2 of them actually. I wrote 1/2 x squared plus 2. There are 2 terms because there's 2 pieces separated with addition. I had also written 3x cubed minus 7. Am I off my screen? Not yet. Okay. 3x cubed minus 7, 2 terms because there are 2 pieces that are separated with subtraction. So there's nothing special about what the exponents have to be or whether you need a constant or you don't have a constant, none of that. It's just how many terms there are. And then the last one a trinomial, a three-termed expression. I did an example of that one as well when I listed mine out. 6x squared plus 2x plus 1. And again, this is also quadratic because it happens to have the highest power as a power of 2. But the reason that it's considered a trinomial is because there's 3 terms separated with addition and or subtraction in the problem. So we would call this a trinomial. All right, I'm going to show you 2 different ways to solve trinomials specifically. There are other methods. These are the 2 that I'm choosing to teach to you. If you choose to use another method, that's fine, but understand that you're on your own for if you make a mistake, trying to figure out what the mistake was, that kind of stuff, or the Success Center to help you. These are the 2 that I'm going to focus on because they lend themselves so nicely to other pieces of information we work with this semester. So the first method that I'm going to show you is called the AC method. The AC method is very friendly. It works all the time without fail. And it hinges on the idea that there are numbers that can multiply and or add to work things out properly. So here's the way it works. We've got our first example, u squared minus 7u plus 10. So the AC method says to take a times c. So the a term is the one that's multiplied by u squared. That's 1 here. The c term is the one at the end. That's the constant. That's a 10 here. And we will get 10. Agreed? 1 times 10 is 10. The b value is the coefficient in the middle. We're just going to identify it. It's negative 7. Okay, so I am showing you the AC method on this one. I do realize that some of you are like, why is she going to all this trouble? Because you're about to see it's a little bit of trouble. And it's not necessarily like the best example of why you would want to do this, but it's a very simple case to see the mechanics of it working. Okay, so just bear with me so you can see it working and see what's going on. So what we want is we want 2 numbers that multiply to give me, that says time. Okay, so this is multiply. They multiply to give me 10, and they add to give me 7. Well, not 7, negative 7. So what are 2 numbers that multiply to 10 and add to 7? Right, negative 5 and negative 2. They both need to be negative, otherwise I won't get a negative 7. They both need to be negative, otherwise I won't get the positive 10. They do multiply to 10, and they do add to negative 7. These are the numbers that I need. So what am I going to do with them? Well, I'm going to take this middle term, this negative 7u, and I'm going to separate them using these values. So it looks like this. I still have my u squared. It doesn't matter whether you put the 5u in front or the 2u in front. It will work either way. And then we have plus 10 equals 0. We're just breaking apart negative 7u into 2 different pieces that add to negative 7u. I'm allowed to do that. And what we're going to do next is something called factoring by grouping. So I'm going to group the first 2 terms and the last 2 terms together. And I'm going to do what I did back on the first problems, right? Well, problem 3 and 4. I'm looking for a common factor. What do u squared and 5u have in common? U. And if I take out a u, I'm left with u minus 5. Everybody good so far? What do negative 2u and positive 10 have in common? They have a 2. And I actually need them to pull out a negative 2. You'll see why in a moment, but just trust me, we need a negative, pulled out 2. If I take negative 2u and I divide by negative 2, what do I get? U. And then if I take 10 and I divide by negative 2, what do I get? Negative 5. So here is why I needed to pull out the negative. My goal in the AC method is to get 2 factors that are identical. The parts in the parentheses should match. If they don't match, there's an error somewhere. Maybe you broke your numbers apart wrong. Maybe you factored something wrong. Maybe there's a negative you forgot to pull out or you pulled out when you didn't need to. All right? Those two pieces have to match or you've made a mistake. Now, consider this whole thing and this whole thing. They have something in common, namely the part that's highlighted in yellow, right? Both of them have a u minus 5. So just like before where I pulled out the u and I pulled out the negative 2, I'm going to pull out all of what they have in common, which is the u minus 5. So if I pull out a u minus 5 from this piece right here, what will I have left? A u. And if I pull out u minus 5 from this piece right here, what will I have left? I will have a negative 2 left. And this equals 0. I think it's worth noting, because I don't want you to look at it and think, well, she's really just making us do a whole lot more work, because it's worth noting that that negative 5 and that negative 2 are showing back up here again. That only happens here because this coefficient in front is a 1. When we get to our next problems, like not tomorrow, but Tuesday, there won't be a 1 at the beginning and it won't work out so pretty. Those numbers won't just show back up down there again at all. We'll have something else happening. So for right now, it works out kind of simply, and you're like, well, there's just the negative 2 and negative 5, and we went through all that factoring stuff. What was nest y? Why did I do that? Well, because it's going to lend itself to something else later on where those numbers don't show up quite like that, okay? But at this point, we're able to finish the problem. We can set each part equal to 0. So u minus 5 equals 0. U minus 2 equals 0. We'll add our 5. So u is 5, barely on the screen still. Add my 2, and u is 2. So we end up with two solutions. U equals 5 and u equals 2. And again, if I wanted to confirm, I could check them back in the original equation, the one before I factored anything, like this one way back up here. If I plugged in 5, I should end up getting 0. If I plug in 2, I should end up getting 0. Okay? Just out of curiosity, has any of you seen the AC method before? Okay, I've got a couple of nodding. Some of you knows. I never saw it until I started teaching. New methods come about all the time. So another method you may have seen before, it's not one I teach, it's called slide and divide. It's not a method that I was taught either. I'm going to show you one more time with the AC method, and then we're going to try one other method, the one that I actually was taught, and I suspect some of you were too. So the AC method, again, remember, says I multiply A times C. Well, right now, A is the very uninteresting number 1. C here is 25. So I have 25. And my B value this time is 10 in the middle. So I need two numbers that multiply to give me 25 and that add to give me 10. That's, yeah, both of them are 5s, right? 5 and 5. Yeah, 5 and 5 are what's going to do it. So what we're going to do then is we're going to take that middle term 10w. So I've got w squared, and I'm going to rewrite the 10w as 5w plus 5w plus the 25. Okay, I group them together where they are. What do w squared and 5w have in common? W. And if I take a w out of w squared plus 5w, what am I left with? Fabulous, w plus 5. How about 5w and 25? What do those have in common? Everybody jointly says 5, right? Yeah, Brady's back there telling me 5. And then if I take a 5 out of 5w plus 25, I have another w plus 5. That's my goal. If it didn't, I would have a problem. I need to go back and find it. So like we said, these two now match. So I look at each of the multiplication pieces in their entirety, and I pull out what they have in common, which is namely the highlighted blue part, w plus 5. So on the first piece, if I pull out w plus 5, I'm going to be left with w. And on the second piece, if I pull out w plus 5, I'm going to be left with 5. This is what I was talking about earlier on, is that sometimes the factors will actually match. So I can write them both down if you wish, right? W plus 5 equals 0 and w plus 5 equals 0. You don't really need to write them down twice, but if you want to, you could. Of course, they will both solve in exactly the same way. So I do get two solutions. They're just the same, which really means I got one solution. The only thing here is that w equals -5. Sorry, I'm almost off my screen down here in the bottom. That's what happens when it projects so large. Okay, and of course, you can take that 5, you can go back up to the original equation that we were first given, plug the 5 in, make sure it works, and it will. That's the AC method. The AC method is far more useful when we get to section 2.3, where I don't have an A value that's 1. When I do have an A value that's 1, one of the methods that's actually very friendly is called trial and error. Trial and error is the only thing that I learned in high school. That's it. I didn't learn any other methods. I've never seen anything else until I started teaching and exploring other things. And maybe that's the school I went to, or maybe that's just the time in which I grew up. I'm not really sure. Trial and error does work pretty nicely when I have a coefficient of 1 at the beginning, though. So let me show you how trial and error works. For trial and error, we actually start right off the bat by making parentheses. And we work with the outer pieces, like this. So the first piece says u squared. So I need two things multiplying together to give me u squared. Well, u and u. It's one of the reasons that the trial and error works so nicely when my coefficient's 1, is that I don't really have to make any choices. It's determined for me. At the end, I do have to make some choices, because 10 itself does not have just one way you can get a 10. We could multiply 5 and 2. We could also multiply 10 and 1, right? So I do have choices, but not a lot of them. There's definitely worse numbers that I could be working with at the ending value. So we need two numbers that multiply to give me 10, but then in the middle, they add to give me -7. We already talked through these, so you already know what those numbers are. They're -5 and -2. Now, this sign at the end, the fact that 10 is positive, means that the signs have to match. The sign in the middle tells me that the signs have to both be negative. So that's how I determine my signs when I'm working with trial and error. So my signs are both negative, and I need two numbers again that multiply to 10 and add to -7. It's -5, -2. Okay, so you can obviously check to see if this is right. We could have done it back in the other method as well by multiplying it all back out, right? First, outer, inner, last, distribution, and so forth to see if it worked out to being what I started with. In particular, what you usually want to be sure of is that the pieces match up. So what do I mean by that? Well, of course, we know that these two are going to equal u squared and these two are going to equal 10. That's how I chose the numbers to start with. But what I really want to check is I want to check that the inner and the outer terms end up giving me the -7u. And they do here, so we're good to go. And then, of course, just like the next step on the last way we did the problem, we'll set each part equal to 0 and solve. So add my 5. So u is 5. Add my 2. So u is 2. And I have two solutions, 5 and 2. Okay. So out of curiosity, how many of you, at least somewhere along the way, somebody did trial and error as a method for finding the factors? Okay. I see a few hands on that one. Like I said, that's the one that I'm most familiar with because that's the one that I did when I first started doing it myself. All right, the other one, we'll do the same thing. So trial and error means that you set up the parentheses just like from the get-go. And again, I've got w squared at the beginning. Well, it means I have to have w and a w. My positive at the end means the signs have to match. And the positive in the middle tells me that they have to both be positive. Yeah, and then I need two numbers that multiply to 25. Again, I don't have a lot of choices. Trial and error also works better. It's a lot easier when you have few choices. I mean, like 25 is a great number, 10 is a great number. 24 is not a great number. It's awful, actually, because you have 1 and 24 and 2 and 12 and 3 and 8 and 4 and 6. 4 choices is a lot of choices when it comes to figuring out factors. So 2 choices, not too bad. It is 5 and 5. So 2 numbers that multiply to 25 and add to 10, that's 5 and 5. And then setting each of them equal to 0. Of course, they work out the same way, just like last time. And w will equal only -5 because it's a duplicate value. Okay, so here's the deal. You're going to have questions that are going to ask you to factor and solve whatever the trinomials, just like the directions say on this. I don't care what method you use. It matters to me not at all. Use trial and error, use the AC method. If you have another method like slide and divide or something like that that you like, use those. It's cool. Whatever is okay with me. But if you have any questions or concerns about how to process through that, please ask, all right? Because you have choices. The last thing that we're going to do in this section is we're going to reverse the process. So we're going to take information and sort of work our way back up the way that we came before. So it would kind of like be taking these equations and saying, on number 7, the solutions are 5 and 2. What's the polynomial? That's what we're going to do. On number 8, the solution is -5. What's the polynomial? And we're going to find the polynomial. So the way that we do that is very much like we're doing everything in reverse. So you'll notice, for example, this always is one of the places of confusion. You'll notice that if it says u minus 5, it ends up being u equals +5, right? And if it says w plus 5, it ends up being w equals -5. The signs switch, right? Because I'm adding or subtracting to move it on between sides of equations. So that's something that's a useful piece of information as we're taking a look. This slide is not constructed well. I'm going to have to scratch out number 10 and do it on the next page. But let's just do number 9 and pretend like number 10 is not there for the moment, so I have space. And hopefully, yeah, I think you have more space than I do. I think you'll be okay. But if not, you got lots of space below it. All right, so the first one here wants us to have roots means solutions, that are 6 and -3. So 6 means I'm going to have an x minus 6. -3 means I'm going to have an x plus 3. The signs switch. And again, the reason for that is because this is saying x equals 6, and I'm moving it back on the same side, so I now have x minus 6 equals 0. That's what's happening really behind the scenes. That's how and why the signs are switching. Now this part at the end where it says the leading coefficient of 4, that simply means there's a 4 multiplied by all of this at the front. We are supposed to be creating a quadratic equation. Equations have equal signs, so this is going to be set equal to 0. And we're going to multiply it all out. Okay? I would do the 4 last. The 4 is just going to make values bigger. I don't want to work with anything bigger than I have to, and so I usually do that at the very end so that I have to work with it for fewer steps. So my suggestion would be to do the distribution in the middle first. So x times x is x squared. X times 3 would be 3x. -6 times x is -6x. And -6 times 3 is -18. Okay, so far so good? All right, so in the middle you should be able to combine like terms. Positive 3x and -6x is what? Yeah, -3x. Minus my 18 equals 0. And then my last step will be to distribute the 4 through. So I have 4x squared. I have 4 times negative 3x, which would be negative 12x. And then I have 4 times 18. What is 4 times 18? What is it? 72? I have absolutely no idea. Is that right? Yeah, that's what I saw on my paper too. Good. So negative 72 equals 0. And this would be the answer that we are looking for. Does that make sense? Okay, I'm going to go to a blank slide on the next one so that we can do the last problem. On number 10, it says that my roots are 5 and 2, and the leading coefficient is 2. Those are the details from the previous screen. Okay, so if the roots are 5 and 2, what are my factors? Right, x minus 5 and x minus 2. The leading coefficient of 2 means there's a 2 at the very beginning. And I'm supposed to be creating equations so they're equal to 0. Okay? So we're going to multiply things out. My x times my x would be x squared. And my x times my negative 2 is negative 2x. And we're going to do the negative 5 times x, which is negative 5x. And negative 5 times negative 2, which is 10. That should look familiar. We've actually seen that polynomial today. Equals 0. Those two, of course, are like terms. So I've got a 2 at the beginning. I have x squared minus 7x plus 10. And then the final step is to distribute the 2 through. So 2x squared minus 14x plus 20 equals 0. Any questions about that one? Okay.